All right, ladies and gentlemen. Today, a lot of what you're seeing actually isn't in your trig book. It is actually out of the pre-cal book because the pre-cal book throws in problems that you're going to see in calculus more frequently. So this is actually stuff that you'll see again in calculus, some of the techniques that we use in calculus to help simplify equations. And multiplying by the conjugate is a big skill for calculus. We do it all the time. What is the conjugate here? Radical 5 plus 4 and radical 5 plus 4. Conjugate means to change. Like when you conjugate a verb, you change the form. This is the same. We change one thing. We change one sign, and that is the conjugate. And from there, we can multiply. So I'm just going to go ahead and distribute in the numerator. We would have 3 radical 5 plus 12. And then something very, very special happens in the denominator. Radical 5 times radical 5 is 5. What happens to the outside and inside products? They cancel out, and that is the best thing about conjugates. And then last times last is negative 16. And so we get 3 radical 5 plus 12 over, we'll say negative 11, which is a fine answer. Okay. So we are doing that very, very same thing today, but with trig equation or expressions. Oh, yes. This is called accessing prior knowledge. All right. Example 1, multiply by the conjugate to establish the identity. You'll like today's worksheet. It's nice and formulaic. Oh, no, it's in handwritten. But it's good. It's hard enough trying to keep up. Right? Yeah. All right. Example 1, multiply by the conjugate to establish the identity. So again, we have an identity. What does identity mean?
Make sure both sides are equal.
They are equal. They are identical to one another. And what we want to do is we want to show the math. How do you go from one side to the other? What algebra do we use so that we can show that these two things actually are equivalent? Now, we can always show it using our calculators. We can put the left-hand side in Y1 and the right-hand side in Y2 and say, look, they match. They're identical. Identical. So, but that isn't an algebraic proof, and that's what we're sort of kind of learning how to do. So a couple things. This side looks more complicated to me because it is a fraction, and over here is not. Okay. I also notice I'm not going to rewrite things in terms of sine and cosine because I have cotangent and I want a cotangent. I have cosecant and I want cosecant. So I don't want to get rid of those because I want them. Okay. However, I do notice a couple of things that have changed. First of all, this is no longer in the denominator. It's been pulled up to numerator, and the signs are switched. And because I'm noticing all of these things, particularly switching the signs, that's a clue that we are going to want to multiply by the conjugate. So even though the directions said it, there is some logic that's happening too. I'm going to multiply top and bottom by the cotangent of x plus cosecant of x. And I'm minus, thank you. Yes, the conjugate changes the sign. So minus cosecant of x on top and bottom. Cotangent of x minus cosecant of x on top and bottom. Yes, you could actually multiply by cosecant of x plus cotangent of x, top and bottom. Yes, you can work both sides. You have to do top and bottom. Yeah. Because that's 1, so that's allowed. But yes, you could do the other side. Yes, you can work either side of the equals. So now, in my numerator, look, I have 7 quantity cotangent of x minus cosecant of x, which is kind of close to what we have here. That's kind of interesting. On the denominator here, what is cotangent of x times cotangent of x? Cotangent, oh, whoops, I don't know what I'm writing. Cotangent squared of x. And what happens to the outside and inside products? They cancel out, and so last times last is going to be negative cosecant squared of x. Do you hear the bells? Ding, 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 ding. Is it 1? Negative 1. I don't know. So what is our Pythagorean? Because there's no magic happening in my brain where I know the exam. I work through it, right? So what is our little phrase that we have? Cot plus 1 equals cozy. Okay. Cotangent squared theta plus 1 equals cosecant squared theta. So cotangent squared of x minus the cosecant squared is
1.
Negative 1. Very good. So that turns into negative 1. So we have 7 quantity cotangent of x minus cosecant of x all over that, bless you, Pythagorean identity of negative 1. Negative 1 is important because what we're noticing here is this is not quite what we want to equal. Here, cotangent of x is first and positive. This one is negative. Cosecant, our cosecant is negative, and here it's positive.
It's over a negative.
Yes. So I'm going to rewrite this slightly differently. I'm going to say if I'm dividing by negative 1, here's one way you can think about it. You guys might be beyond this, but I don't know. Isn't dividing by negative 1 the same as just having negative 7? Yeah, okay. And then I think what I want to do is actually just distribute the negative. What? Okay. So I can leave the 7 alone, and I can distribute the negative, and that would give me negative cotangent of x plus cosecant of x. And now those match. So there's lots of ways to do that sort of stuff, that sort of simplifying with negatives. It's kind of a weird thing. Is it okay that they're not in the proper order here? All the signs match, yeah. So this is the idea that 4 plus 5 is the same as 5 plus 4. That's the commutative property, they're fine as long as all things are consistent. Okay, so that wasn't too bad, right? Okay. Example 2. Use the trig substitution to write the algebraic expression as a trig function of theta. So theta is the transient part. Okay, so there's a lot of vocabulary going on in these instructions. My son is so cute. He's a builder. He builds everything. But he calls instructions constructions, which is so adorable. And I don't know how many millions of times I've corrected him, but in a way, he has a good thinking in that we are constructing meaning from something. And so it's important to understand the vocabulary. First of all, we have a trig substitution. Right here is the trig substitution. They're saying x is the same as 2 tangent of theta. So there's the trig part, and we are literally going to substitute it in place of x. With the algebraic expression. The algebraic expression is right here. This is the algebraic expression, the square root of 4 plus x squared. All under that radical. So that is an algebraic expression because it's made up of letters and numbers and operations. And there's no equal sign. It's just an expression, okay? And what we are doing is literally substituting, and that's all we're doing here. And again, I said this is stuff you'll see in calculus, and it is literally called a U substitution, and we do it a lot. So we are going to take tangent of theta and replace our x with that 2 tangent of theta because they're equivalent. So 4 plus 2 tangent of theta, and then we're squaring that. Yep.
Also, just to do the square root, like just maybe 2 plus x.
We can't take a square root because it's not an equation, so we can't square root both sides. Does that kind of make sense? We have to maintain our algebraic integrity. So we cannot. Okay, so here's another question. So here is the most common question. 5 squared is equal to 3 squared plus 4 squared. Is this a true or false statement?
Is it true?
9 plus 16.
Wait. No, that's true.
It's true, right? So this is 9. 9 plus 16 is 25. Okay, and this is 25. So the true statement, as it is, this equation is true. And this is the number one algebraic mistake of all time. Can we blanket square root? Willy-nilly. I want to square root both sides. So then the question is, if what you're thinking is the square root of 5 cancels out, and here all those squares cancel out, so we're left with, is 5 equal to 3 plus 4? No. Can you blanket square root?
No.
90% of the time you cannot. Watch what happens when we do this problem. So we're substituting in place of x, and I'm going to square 2 tangent of theta. So what is 2 tangent of theta? Quantity squared. 4 tangent squared theta, yeah. So 2 tangent of theta times 2 tangent of theta. 2 times 2 is 4. Tangent times tangent is tangent squared. Okay. So then when I look at my expression now, I see something in common. What do they have in common? A 4. So I can factor out a 4. So that becomes, when I take out the 4, what's left?
So now you can then bring that out.
Oh, close. We're almost there. You're thinking correctly. What is 1 plus tangent squared? 1 adds a tan by the secant squared theta. That's interesting. So now we have 4 secant squared. Now, what changed? Jonah, you said now we can do the square root.
4, yes.
Okay. Because it's a product, now we can do square roots of things. What is the square root of 4? 2. What is the square root of secant squared? Secant of theta. Yeah. So now that it's a product, so what we did was we used some trig to manipulate this expression, and we went from addition, and using factoring can rewrite it so then it does simplify to something fantastic. Okay. And this is all honest to goodness algebra that's really, really, really powerful. And this is the most common mistake ever. Okay? We cannot take square roots across addition or subtraction 99% of the time. All right? Sometimes, like this, we have a substitution and we can do some factoring. Then, once things are products, then we can use square roots. Okay? Exactly. A plus B does not equal C. That's right. It also doesn't create a triangle either. So when you think about having a triangle, if A plus B equaled C, does it actually create a triangle? Would it have a roof, or would it fall flat? It falls flat, right? If you have 3 inches and 4 inches and 7 inches, would it have a roof? No, it would just fall flat, right? So 3 plus A plus B does not equal C. A squared plus B squared does equal C squared in a right triangle.
You still make a root. It's not very good.
No. The rule for triangles is that A plus B has to be greater than the third side. The sum of any two sides has to be larger than the third. Yeah. Lots of geometry. All right, example 3, verify the identity with the LCD. Sample 3, verify the identity using the LCD. What is LCD? Lowest common denominator. Now, I think there's like 4 problems on the back of today's worksheet that 2 of them are very similar to what we're going to do here, and then the other 2 are different. Okay, so using LCD is a mere suggestion. The problem with identities is that there are literally a million different ways you can do it, and I have seen some very creative stuff. And so I'm always going to ask you, well, what do you think you want to do, and go with your train of thought. But it's hard. It's hard to tell someone else what to do because they're not thinking along your same wavelengths, right? So it can be complicated. So there's lots and lots of ways to do things. But one thing I notice is I've got a couple of trig functions here, but I'm going to go ahead and trade out that secant of x for 1 over cosine. Can I do that? What I've just created is a complex fraction, which, well, we just got more complicated. But what I want to do is think about using the LCD. This has a denominator of cosine of x. And what I want to do then is I'm going to multiply top and bottom by the cosine of x. Okay, watch what happens. So I'm going to go ahead and distribute in my numerator. What is cosine of x times 1 over cosine of x? 1. And cosine of x times negative 1 is negative cosine of x. And now in my denominator I have cosine of x times 1 minus cosine of x. You'll notice I didn't distribute that one. Why not? Yeah, 1 minus cosine of x reduces on top and bottom. And we get 1 over cosine of x, which is secant of x. Isn't it crazy? I find this stuff really like, oh, wow, look at that. It's amazing. It's all related. Everything with triangles is related. Oh, it's confusing. It takes a long time. I've been doing this for a long time. Okay. Do you have questions for me? Okay, that's it.
It's like a dream.